All right, so this is section 10.2, day one. This will definitely be a multi-day, multi-video lesson. We are now going to start talking about the calculus using parametric curves. So 10.1, we talked about all about parametrics and how that works, and now we're going to apply the calculus to it. So just like everything else um, in rectangular, we have calculus that we can use with parametric curves. The first and foremost that we're going to talk about is slope. Parametric curves have slope just like everything else does, depending on where you are on the curve. So let's discuss how to do this. And to be honest with you, this one really should probably be one of the easier ones to figure out. Remember that with parametrics, your x's and y's are now both functions of some other variable. And in our case, we're going to go with t for the most part. Doesn't always represent time, but that's just kind of a generality. So the slope of a curve at some given point, xy, is going to be given as still dy over dx. However, in parametrics, remember that dy is dy over dt. The change of y in parametrics is going to be the change of y with respect to t, and then over dx dt. So think about it, if you do, it's just dy over dx. It's the change of y over the change of x. However, it is with respect to time. Therefore, it is dy over dt over dx over dt. Provided, of course, and it says it right there, that dx over dt does not equal 0, because if that is the case, you have an undefined slope. So it does not mean that you don't have a potential tangent there. It just means that it's vertical or an undefined slope. So dy over dt is the derivative of the y piece. Dx over dt is the derivative of the x piece. Pretty straightforward, I think. At least I hope so. Hopefully that makes sense. It's still basically a change of y over a change of x. All right. So let's go ahead and calculate a couple of these. If we want to find dy over dx, where x is defined to be t plus 1 over 2, and y is defined to be t minus t squared, again, both parametric, it is relatively simple in the fact that it is dy over dx is dy over dt over dx over dt. So we basically just need to find the derivative of the y portion with respect to t, and then divide that by the derivative of the x portion with respect to t. So the y portion, the derivative with respect to t, is 1 minus 2t, basic power rule. And the derivative of the x portion with respect to t, be careful on this. You don't need to use a quotient rule, even though it looks like a quotient. Remember that that 2 on the bottom is a constant, so technically you could divide each term by 2, or you could throw 1/2 out into the front, and really that would just make x 1/2 of t plus 1, which means if you distributed that 1/2, you would just have a derivative with respect to t of 1/2. And then if you just want to clean this up, since we're dividing by a fraction, we'll multiply the top and the bottom by 2. So you would get 2 minus 4t. And that would be your dy over dx. And the interesting thing about that is dy over dx is in terms of t. And that is okay. All right, let's try another one. Example 2. Dy over dx is what we want to find given the parametric equations that are given there. So again, it is dy over dt over dx over dt. So the derivative of the y portion with respect to t will be 2 cosine of t. The derivative of the x portion with respect to t will be negative 6 sine of t. And then just doing a little bit of simplification, the 2 over the negative 6 becomes negative 1/3. And cosine of t divided by sine of t is cotangent of t. So we get negative 1/3 cotangent of t. All right, I hope that those two are pretty straightforward. Move on to number 3. A curve is defined by the parametric equations given as x equals 5t squared minus 7t and y equals 1/3 t cubed plus 6t. What is the slope of the tangent line to this curve at the point where t equals 2? So the only difference here is now we are actually finding this at a particular t value. Everything else is going to be the same. So dy over dx, this time at t equals 2, is going to be dy over dt. Well, that's going to be, bring down to 3, that's going to be t squared plus 6 divided by dx over dt, which is going to be 10t minus 7. And once again, evaluated at t equals 2. Just plug in t equals 2. What's that? 4 plus 6 is 10 on top. 20 minus 7 is 13 on the bottom. So at that particular t value, the slope is 10/13. All right, moving on. Number 4, what is an equation for the line tangent to the curve with parametric equations given at the point where t equals 3? So this time they're actually asking us for the equation of the tangent line. And typically we want that written in rectangular unless it says otherwise. So we're going to have to put this into terms of x and y, but that's not going to be too difficult. In order to find the x and y values, because we're going to need those for point slope form, we just plug in t equals 3 into the given equation. So we know that our x value is 1/3, and the y value, plugging in 3, is going to be 2. Square root of 4. So let's find the slope. We have x, y, we need slope to write the equation of the tangent line. So dy over dx at t equals 3. The derivative of the y portion. So t plus 1 to the 1/2 will become derivative 1/2 t plus 1 to the negative 1/2. Chain rule times the derivative of t plus 1 is just 1, so we don't need to worry about writing that. And then the derivative of 1 over t. Remember that 1 over t is the same thing as t to the negative 1 power. So power rule, bring down the negative 1, subtract the power by 1. So now we're just going to go ahead and plug in 3 and see what we get. So we are going to get 1/2 of 4 to the negative 1/2 over negative 3 to the negative 2 is the same thing as 1 over 3 squared, so that's negative 1/9 there. So let's see, 4 to the negative 1/2. 4 to the 1/2 power is 2, but negative 1/2 makes it a reciprocal, so that's going to give us 1/2 times a half on the top, so that's a fourth, divided by negative 1/9, so we should get negative 9/4 for our slope. So now we're just going to use that information, plug it back into the point slope form, and we'll have our equation of the tangent line at the given value when t equals 3. So that should be y minus 2 equals negative 9/4 x minus 1/3. And again, that is perfectly fine to leave that way. All right, number 5. Calculate the slope of the curve given by the equations x equals e to the t and y equals cosine of 3t when t equals 2. Again, all this is the same idea. This just has some slightly different things to look at. As far as derivatives, we want to evaluate that at t equals 2. So the derivative of the y portion goes on top. That's going to be negative 3 sine of 3t, utilizing a chain rule. Make that a little bit better. Sine of 3t divided by the derivative of e to the t. It's just e to the t. And we'll evaluate that when t equals 2. So we are going to get negative 3 sine of 6 divided by e squared. Okay, that's not a real pretty derivative, but that is the derivative. All right, moving on to the next one. Example 6. Write the equation of the tangent line to the curve given by the given parametric equations at t equals 2. Well, if you recognize this, this is exactly the same problem that we just did. No reason to redo the whole thing. We know that dy over dx was, at t equals 2. was negative 3 sine of 6 over e squared. So really all we need to write the equation of the tangent line, because we now have the slope, is the x and y values. So let's see, x is going to be e squared, y is going to be cosine of 6. Plug all that stuff into point slope form and we are good. Y minus cosine of 6 equals our slope, which is negative 3 sine of 6 over e squared times x minus e squared. And that is the equation of the tangent line. All right, so the idea behind taking finding the slope is just taking the derivative of the y portion, the derivative of the x portion, all with respect to t, dividing the change of y over the change of x, and if you have a value, plugging it in. So that's pretty straightforward, I think. The second derivative is not quite as straightforward, although it's not terribly difficult. There is one main thing you have to remember. So the second derivative, and the notation for that is this right here, d squared y over dx squared. There is actually a reason for that, which I am not going to go into right now as far as why that notation is the way it is. If you kind of look at the second or middle piece, it might explain why that is. You're actually taking the derivative with respect to x of a derivative of y over x already. So that's what you're getting. But there's an extra piece to this. So what you have to do is you have to take the derivative of your first derivative, just like you normally would, but then you have to divide whatever that answer is by another dx over dt. Okay, this right here is different. Okay, we don't usually have to do that with rectangular coordinates. You just take the derivative as it is of the first derivative and you're good. Well, this one you have to take the derivative of the first derivative, but then you have to divide it by another dx over dt. And this is going to take place for any higher order derivative in parametrics. If you were doing the fourth derivative, you would have to take whatever you got as the third derivative, you have to take its derivative, and then you would have to divide by another dx over dt. That will occur every single time for a higher order derivative. You will have to divide by an extra dx over dt. So just don't forget that part. And it says it right here. You take the derivative of the previous derivative and divide it by another dx over dt. So that is the rule for higher order derivatives in parametrics. Again, not terribly difficult of a concept, but can get kind of messy with higher orders. So let's take a look. So if x is t squared minus t, y equals e to the 2t, we want to find the second derivative at the point where t equals 2. In order to find the second derivative, we have to get the first derivative first. So let's change the colors. Let's go orange here. So we're going to do dy over dx, which is the derivative of the y portion, derivative of e to the 2t, again using a small chain rule, is 2e to the 2t. The derivative of the x portion is 2t minus 1. So that's dy over dx. Now we need to take the derivative of that to get the second derivative and divide it by another dx over dt. So we will get d squared y over dx squared. It's the derivative of what we just found. So now we will have to incorporate a quotient rule. So let's see. The derivative of the top is going to be 4e to the 2t times the bottom minus the derivative of the bottom, which is just 2, times the top, all over the denominator squared. Okay, that's just the quotient rule portion. Because this is a second derivative, we have to remember to divide the whole thing by another dx over dt, which we've already found, because that's what this is. So we divide it by another 2t minus 1. So ultimately, that becomes 4e to the 2t times 2t minus 1 minus 4e to the 2t over, So we're going to have 2t minus 1 squared times another 2t minus 1 in the denominator. So we get 2t minus 1 cubed. And then we want to evaluate that when t equals 2. So our second derivative evaluated at t equals 2 is what we get when we plug t equals 2 into that thing on the right there. That is going to be, let's see, plugging a 2 into here is going to give us 4 minus 1 is 3, times the 4 out in front is going to give me 12, e to the 2 times 2, e to the 4th, minus 4e to the 4th, well that'll simplify, over, plugging a 2 into the denominator is going to give us 3 cubed, which is 27. So it looks like we are going to get 8 e to the 4th over 27. And that is the second derivative. And as you might expect, it does have something to do with concavity and everything like that for application purposes. We won't really get into that right now, but yes, that is what that has to do with. All right, let's see, number 8. Just determine the second derivative of the given curves. So let's just go through that process. There's nothing to plug in here, so this is just going to be an algebraic derivative. So we're going to have dy over dx is derivative with respect to t of y is going to be negative 3 sine of 3t. Derivative with respect to t of x is e to the t. Second derivative, again, a bit of a quotient rule here. So the derivative of the top is going to be negative 9 cosine of 3t times the bottom, e to the t, minus derivative of the bottom, e to the t, times the top, negative 3 sine of 3t, all divided by the denominator squared, divided by another dx over dt, which is e to the t. So the nice thing here is, if you can see this, great. If you have to multiply, you can always make that over 1 and, multiply the reciprocal of the bottom fraction. You're going to introduce another e to the t in the denominator, but what you should see is that I have e to the t in both of the numerators. So really what's going to happen is that one will all cancel with that one. And what we are left with here is negative 9 cosine of 3t plus 3 sine of 3t divided by e to the 2t. All right, video is running a little bit longer than I wanted to, but I think we're actually going to be able to complete this one, so that's good. Because the last thing we have to talk about is finding horizontal and vertical tangents. And really, again, this should make sense because it's the same principle that we had before. If you have a horizontal tangent, that means that the derivative itself is 0. And if the derivative here in parametrics is going to be 0, that means your numerator must be 0. So the dy over dt portion has to be 0. As long as dx over dt is not 0, then you have a horizontal tangent. They can't both be 0. You're going to have a vertical tangent when you have your denominator equaling 0, because that would be an undefined slope. So it would be a vertical line. And again, that's going to happen when dx over dt equals 0. Again, as long as dy over dt does not equal 0. So that's what you're looking for with horizontal and vertical tangents. And our one example here says, a particle moves along a curve in the xy plane according to the equations that are given. What are all the values of t for which the tangent line to the particle's path is vertical? So we are looking for a vertical tangent line and the values that that's going to occur at. So we are looking for where dx over dt equals 0. Well, let's figure that out. Dx over dt. First thing we need to do is find that. Well, dx over dt is going to be 3t squared minus 6t. We want that to equal 0. So let's set that equal to 0 and solve. So we can factor out a 3t. And it looks like our t values would be at 0 and at 2. And remember, the idea behind this is as long as the denominator dx over dt equals 0, you'll have a vertical tangent as long as the numerator's derivative dy over dt also does not equal 0 at one of those values. So there's two different ways you can do it. One way or the other, we need to find dy over dt. So let's do that. dy dt is going to be t squared minus 4. So now you can either set this equal to 0 and figure out where the overlap is, or you can just plug in 0 and 2 into that, and if one of them gives you 0, then you know you've got a problem. And hopefully you can see that by plugging in 0, you would get negative 4 into dy dt. If you plug in 2, you would get 0, and that's a problem. So 2 cannot work. T equals 0 is the only solution where you would have a vertical tangent, or a vertical part, the path of the particle would be vertical. All right, I think that is plenty enough for this video. We will come back with day 2.